today we will be answering another problem. So, question for number 2 is an image smoothing operator is modeled by a linear transformation defined by. So, in letter 8, write the matrix representation of T. To find the matrix representation A, we look at how the operator acts on each component of the vector. So by applying this linear transformation across the entire vector, we effectively blur the sharp jumps in data, resulting in a smoother, cleaner signal. Our goal today is to translate this mathematical rule into a formal matrix representation. As derived previously, the matrix A for this transformation is a tridiagonal matrix. Since the boundary condition are zero, the first and last rows only have two non-zero terms.
So, yt is linear. To know how it is linearity, there are two conditions that are needed to be satisfied, and that is additivity and homogeneity. And additivity is x plus y equals tx plus ty. This is additivity. Ayan. And the second condition is the homogeneity, which is alpha times x equals alpha t x. Yan. This is the second condition, the homogeneity. Yan. So now let's check. Let us consider an example that we are given with function t from Rn to Rn defined as tx I equals 1/2 xi plus 1/4 xi minus 1 plus 1/4 xi plus 1. Ayan. So, now let's check. We evaluate it with ano yan? Now let cut nyo yan. Now let x and y be an element of Rn, and now we evaluate it as t x plus y tapos I equals wait, cut na yan. Sige, cut na yan. Wait. Now, let us consider an example. We are given with function t from Rn to Rn and defined as txi equals 1/2 xi plus 1/4 xi minus 1 plus 1/4 xi plus 1. And now let x and y be an element of Rn, so we evaluate it as tx plus y, then I equals 1/2 xi plus yi. Plus yun, plus. Ayan. Now, as we observe, we can distribute these terms. So now, this becomes equals 1/2 xi plus minus 1 plus 1 plus 1/2 yi plus 1/4 yi minus 1 plus 1/4 yi plus 1. Then, but notice that the first group is exactly tx and the second is ty. Therefore, we can make this like tx I plus ty I. And there we go. And since since this holds every component I, we can conduct that this is tx plus ty. Ayan. So, we can check that that the for so, so that we can cut nyo na lang yung voice, pwede naman yan. So now we can conclude that the first condition is 1 is satisfied. Ayan, no? Ayan. Hindi ko alam kung tama ba yung ginagawa ko nito. Now now let's check the second condition. First, we evaluate T alpha x I equals 1/4. Mali. Now let's check the second condition. First, we evaluate plus 1. And now as we observe that each term contains the scalar alpha. So we can factor it out and give us alpha 1/2 xi plus 1/4 xi minus 1 plus 1/4 xi plus 1. There we go. But this expression inside the parenthesis is exactly tx. So we can get alpha t xi. And just like before, that the I is also in every expression, we can conclude that this is alpha t x. Ayan. So, So now we satisfy the second condition. Ayan, satisfied na yung second condition. So that's why the given is so that's why function t is a linear because we satisfied two conditions.
An image smoothing operator is modeled by a linear transformation T from Rn to Rn defined by Txi equals 1 half xi plus 1/4 xi minus 1 plus 1/4 xi plus 1 with x0 equals xn plus 1 is equal to 0. Thus repeated application of T increase or decrease noise. Explain using linear algebra. The operator T from Rn to Rn can be written as this, containing 1 half, 1/4, and zeros. An x element of Rn can be expanded in the eigenbasis. X equals the summation of Ck, Vk from k to n. The application of T repeatedly gives us Tmx equals summation of Ck alpha Kem Vk from k to n. The repeated application of T suppresses components and therefore it reduces noise. That's all. Thank you for listening.
Alright, let's start. To analyze this operator using linear algebra, we first represent the transformation T as an n by n matrix A because each pixel is an average of itself and its neighbors. The matrix is tridiagonal. So nandito na siya. The matrix has 1 half on the main diagonal and 1/4 on the sub and super diagonals. So we can check the sums of the rows to see if the operator expands or shrinks the data. For any integral row, the sum is exactly 1. For the edge rows, it is 0.75. According to Gershgorin's disk theorem, this tells us that the absolute value of any eigenvalue, lambda, is less than or equal to 1. So the sum of the absolute values of the entries in a row is less than or equal to 1, which implies the magnitude of lambda is less than or equal to 1. So the eigenvalues for this specific type of matrix follow a cosine distribution. The formula to the kth eigenvalue is shown here. The important part is that as the frequency k increases, the eigenvalue lambda sub k gets smaller. So, eto, lambda sub k equals 1 half plus 1 half times the cosine of k times pi divided by n plus 1. So, when we apply the operator t repeatedly m times, we are calculating a to the power of m times x. We can write our image x as a sum of its eigenvectors v sub k. And so on. Yan. A to the m times x equals to the sum of constants subs C sub k times lambda sub k to the power of m times the eigenvectors v sub k. So noise is represented by the high frequency components, which have the smallest eigenvalues. Because these eigenvalues are raised to the power of m, they shrink towards zero very quickly. This proves that repeated application filters out the noise while keeping the smoother parts of the image longer. Therefore, the noise decreases. So, as m approaches infinity, then lambda sub k to the m approaches to zero, high frequency noise decays fastest. Okay na yan?
So hi everyone, I am Justin ARAN from BSIT 24, and today I'm going to show you how to model an image smoothing operator using linear algebra and Python. We are starting with this linear transformation formula here, which essentially takes a pixel and averages it with its neighbor. And our goal is to answer question C: does this increase or decrease the noise? And then actually build it in code. So I've actually already created the code here in the VS Code. So first, let's look at the matrix representation. I created a function that builds an n by n matrix. So you can see here I'm setting the diagonal to 0.5 and the neighbors to 0.25. So this represents the weights from the main math formula. And if we're gonna scroll down, we're gonna see the main function. So to simulate the smoothing, I create a noise signal and then run this in loop. So here is the loop. Inside the loop, I multiply our matrix T by the signal vector. So since this is a linear transformation, I can just use the at symbol for matrix multiplication. And now that I've introduced the parts of the code, let's try to execute it. Let's run the script and see if the math actually works. So here you go. So the code executes, calculates the eigenvalues to confirm stability, and generate this plot that you can see on your screen. So this has a lot of lines. So there are uh, broken lines, which indicates the original signal input or the truth, the red lines, which indicates the noisy input, and the blue lines, which are the smooth inputs after 5 iterations. Okay, so to further elaborate, the red line represents our input signal with random noise added to it. You can see how jagged and rough it is. So this corresponds to high frequency variation. So that red lines that you can see. On the other hand, the blue line is the result after applying our matrix 5 times. You can see it has successfully smoothed out the noise while keeping the shape of the wave. So through this graph, we can confirm that the operator acts as a low-pass filter, decreasing noise through repeated linear transformations. So that will be on my part. Again, I'm Justin Jantiaran. Thank you for listening.